our first speaker for the day is Dr. Sergie, who needs no introduction to the hardware security industry. His research always blows my mind, and he has spoken 4 times now with us at hardwear.io. In his talk today, titled Practical Reverse Engineering of Elliptic-Curve Cryptography-based Authentication Device with Zero Knowledge, he will discuss this talk with the target as Infineon Optiga Trust B. And in spite of many countermeasures implemented, it was still possible for him to bypass the security and completely clone the device. Friends, if you have any questions, please share it. See.
Hello, everyone.
One second, Doctor. Friends, if you have any questions, please send them via the Zoom chat directly to the speaker or to me, and we will take it after the presentation is complete. So let's hand it over to Dr. Sergie now.
Hello, everyone. I'm presenting today the joint work with Dr. Markus Kuhn and his PhD student Chun Yu. So we'll talk about the authentication devices normally used to prevent counterfeiting. I will talk about security features that are usually used in those devices, and I will present reverse engineering project of one particular device that based on elliptic-curve cryptography. And then I will present all the milestones we addressed during that process. And finally, we'll talk about the limitations and the future work. So I will first introduce myself. So I'm a senior research associate at the University of Cambridge, and I'm doing hardware security research since 1995. They've tested microcontrollers, smart cards, FPGA, and other secure devices. I have a broad knowledge in the background of chemistry, electronics, physics, and computer science. And in my research, I'm always interested in what I'll call impossible problems, where you trying to address something that others think is not possible to achieve or to do. And I'm always interested in developing new attack methods and testing challenging devices for vulnerabilities. So the counterfeit prevention was based on authentication since mid-90s, and I was involved in analysis of such devices. At that time, it was primarily car industry that relied on security, one of the first industries. And since 90s, many consumables were using authentication that involved memory cartridges in servers and game consoles, printer cartridges, batteries, and of course, medical equipment, the life critical and safety critical systems. So if you look at the history of authentication devices, then in old days, they were very simple without much security, but just based on serial numbers or on devices with a proprietary communication protocol. And for those devices were relatively easy to attack. You just eavesdrop on the communication, or you brute force the interface to the device. Then from early 2000s, the security became much stronger, but still there was lots of security via obscurity with weak proprietary encryption. And most devices were based on symmetric cryptography with TES or AES, or some chips like Dallas 2432 were using SHA-1 hash function for authentication. Attack methods on those devices were much harder. They involved some level of reverse engineering, firmware extraction and analysis, memory probing. And then since 2010, many devices started using asymmetric cryptography. And those devices were designed with security in mind. So they had some countermeasures against side channel attacks, against physical attacks with sensors and memory encryption. And those devices were fabricated with smaller process, usually between 45 and 90 nanometers, with multiple metal layers. And attack methods were required much more work and were much more expensive, the reverse engineering, chip modification, and data bus probing. So why authentication devices switch to asymmetric cryptography? If we look at the process of authentication, then in symmetric authentication devices, first host requests the information, then it sends a random number and device computes hash, for example, and sends it back. And then host has to generate the same hash using the secret inside that host. And if both hashes the same, then the device is authentic. In asymmetric authentication, host requests the same information plus some way of verifying the public key in the form of certificate. Then host checks that the public key wasn't tampered with, and then it computes a random change by multiplying a random number with a base point, for example, for elliptic-curve cryptography, and device multiplies that number with the private key, sends it back, and host computes the public key multiplied with the random challenge and verifies that the both numbers match. So the advantage of that is that if you try to attack a symmetric authentication device, then each device stores unique key, and even if you compromise it, it's not a big deal because the key can be revoked by the manufacturer. However, the host stores everything that needed for producing clone devices. And even if they use key derivation function and not the actual key, then still, if you take full control over the host device, you can ask it to produce as many derived keys and as many signed hashes as you like. And then you can implement the algorithm in a much simpler devices. In case of asymmetric authentication, again, each device stores unique key and it can be compromised and in the same way. However, the host does not store any key. So for an attacker, there's no point to attack the host because it only contains the algorithm to verify the validity of the secret key. And if the devices have big security, an attacker could extract large set of keys and reproduce those set of devices in mass production. However, the disadvantage is that the asymmetric authentication usually requires quite strong computing power, so you cannot use very cheap devices to replicate the actual devices used in real products. So for an attacker, it always aims to bypass authentication without being detected. And ideally, he wants to be able to generate unique device ID and secret key and signatures. But that on practice can only be done with symmetric authentication devices. With asymmetric devices, you can realistically only extract thousands of real sets of ID, secret key, and signatures. So for the manufacturer, it would be easier to spot these compromised devices and disable them. And also for the real world application, if someone tries to come up with counterfeit devices, he needs to make sure that his solution is adequately secure, because otherwise he will face other attackers who will try to compromise the devices with weaker security rather than the real ones. Since we started talking about elliptic-curve cryptography-based authentication devices, there are several manufacturers who offer such chips. For example, Texas Instruments, you can buy those devices from many distributors, and you can buy all the necessary evaluation kits and development kits, so you can easily start making such devices. The same applies to Maxim semiconductor devices. You can easily get them, buy evaluation kits. Data sheets, they're not easily available, but you can find them on the internet. And the same is with microchips. So devices come with some documentation, but the development kits are restricted, so they're much harder to work with and effectively more difficult to attack. Then goes Infineon devices, and devices you can buy from distributors, but the data sheets are very limited because you have to sign an NDA for full data sheet, and they have limited availability of evaluation kits, and all development kits are restricted. The NXP devices, you can buy the devices, but there's no development kits easily available, and again, very restricted data sheets. The ST microelectronics, those devices probably are the most secure because they're based on the real smart card chip with EL5 certification. So in our research, we decided to go after the Infineon device because we thought that this is the biggest challenge we can address. So from Infineon, there are 4 different devices that we found with ECC-based authentication. The simpler one is Origa 1, with only 0.2 kilobytes of EEPROM and approximately 180 nanometer fabrication process. And this device is based on a full logic design. However, there's very limited information about it. Even the datasheet doesn't specify what kind of elliptic curve it uses. Then Origa 2 is the same fabrication process, but CPU-based device. Datasheet specifies 163-bit elliptic curve, and it has slightly larger memory. Then Optiga Trust B is the device with smaller fabrication process, approximately 90 nanometer, as we measured it. And it uses 131-bit elliptic curve. Also, it's a smaller key of the curve. It's still not something you can easily brute force. And again, it's a full logic design. And Optiga Trust E is the same fabrication process, and the much bigger key size of the elliptic curve and larger memory and CPU core. So we decided to go after Optiga Trust B device and see what we can do with it. So these devices, as I mentioned, are available from distributors. We were able to buy the evaluation kit. However, it's not a development kit, so you cannot write your own authentication challenge response and verification of the device, but you can observe what communication is involved with the device. Public datasheet contains very limited information. It's basically package pinout, connection, power supply voltage. They do mention that device uses SWI communication interface, but no information about it. No information about modes of operation, how to access user non-volatile memory. It only mentions that the size of the elliptic curve key, 131 bits for authentication engine, 163 bits for the certificate. So we had to somehow find the information about the communication interface, protocols, how to access the memory, how to use the lifespan counter that is normally used to prevent counterfeiting in printer cartridges, how to verify the signature of the public key, and we had to find all the elliptic curve parameters, and also the datasheet mentioned that the authentication involves some MAC function. So we started looking at the evaluation kit. It comes with the Windows GUI interface, and so you can click on the buttons and get the device authenticated. So on the left picture, you can see what the evaluation kit looks like. And we hooked the logic analyzer to see what kind of waveforms is used for the communication. However, the evaluation kit didn't come with any schematic, so we had no idea what's going on inside. However, we did some internet search, and we found that this SWI interface is based on the MIPI-BIF standard used in batteries. And Infineon had a patent on this interface, and they also proposed a specific use for this interface for data encoding in transactions. So at this point, we were able to start to gain some information. However, we still had to reconstruct the circuit diagram of the evaluation kit, and it had a 4-layer PCB. And usually the multi-layer PCB, you can either use mechanical grinding to find all the layers, but we decided to test what the 3D X-ray CT machine can do from a neighboring department. So just for the curiosity, and it turned out that 3D X-ray can give you all the details necessary to reconstruct the circuit diagram. So that's what we ended up with by drawing all the connections. So the evaluation kit has two microcontrollers. So the right one is only used for USB communication with the PC software, and the left one is handling all the communication with the authentication chip. And then between themselves, microcontroller talk via UART interface. So the microcontroller we were interested in that was talking to the authentication chip is Infineon XMC4500 Cortex M4R microcontroller. And we also, the logic analyzer found that this evaluation kit has a debug interface, debug port, and that debug port prints out all the information about the steps of the authentication process. So on the right side, you can see what the terminal prints out when you connect it to this port of the microcontroller. And the USB microcontroller, the other one is simply sending the commands from the PC directly to this XMC microcontroller. So at this point, we were able to reconstruct the SWI communication. So it normally stays at this high level for idling and after power up, and for power down, it goes to the low state. And then the information is transferred and encoded by the length of the pulse. So the shorter pulse is 0, longer pulse is 1. And the advantage of this is there is no need for stable clock, which is good for small authentication devices without precise clocking. And the first 2 bits are training bits, so it is 0 followed by 1 or 1 followed by 0. So from that point, the device knows the rough communication speed, and that tau can vary between 1 and 50 microseconds. And then it transfers 10 bits of data through the interface, and that allowed us to reconstruct the whole communication process and draw the big table. So he's only part of the table is presented. So we knew what the GUI interface was sending to the device. We knew what the microcontroller was sending to the authentication chip, and at the same time what debug terminal was printing out. So that helped us to better understand the protocol. However, still there was lots of unknowns in the device authentication. So we started looking at the debug port of the XMC microcontroller because it's a standard ARM microcontroller, and we hooked a J-Link JTAG debugger to it, and we found that there's no protection against debugging, so you can download the full memory from the flash inside the microcontroller, and also you can compile your own code using GCC or Dave. We also looked at the Windows GUI interface, the decompiler, but that didn't reveal anything useful apart from the names of the commands. So it was everything inside this XMC microcontroller, and we decompiled the firmware using Ghidra decompiler tools, and that helped us understand all operations and commands and understand SWI and ECC authentication flow. And finally, we re-implemented SWI communication on the Relax Lite kit from Infineon with the same microcontroller. And for ECC authentication, a Python script was used. And later, that was turned into a successful practical course for master students at Cambridge. And almost all students succeeded with replicating all the steps that I've described so far, the writing their own SWI communication and performing the ECC authentication with the authentication device. So at that point, we were able to talk to the device, so we can read the, at the bottom, you can see the response from the device for requesting the device ID, for requesting the certificate, the public key. Also, we were able to print the non-volatile memory. However, as you might notice on the right dump, the large part of the memory contains zeros, apart from the public key and certificate, and that looked quite suspicious because we were expecting to see the secret keys there, and obviously the device had some security to prevent this. So this is SWI commands which are used by the device, and for it has two different memory regions for non-volatile memory and for registers, and also use special commands for ECC computation and checking whether the device is busy or not. With those registers, you can access different operations. They're used for different operations. For example, for ECC, they have dedicated buffers and separate buffers for non-volatile memory access. There are two registers associated with NVM access, where you set certain bits for read, write, or you select the buffer and you set the NVM address. And when you initiate the start of the reading, you get back the actual data that are sent to the buffer. So these are examples of the NVM read and write sequences where you specify the address and you initiate different operations. And for lifespan counter, you only have the operation to decrement that counter. So the next step we did was to reverse engineer the authentication process. So the challenge-response protocol we found was similar to the variant of Brown-Hess-Meyer published in 2008. And that particular protocol is optimized for low hardware footprint. And also in this Optiga Trust B device, the scalar point multiplication uses Montgomery method that was presented more than 20 years ago at CHES. And this method does not require the Y coordinate or curve parameter A. And also the device uses projective coordinates, and that avoids any divisions on the authentication chips and allows randomization of calculations, which is important for side channel attack countermeasures. So here's the example of what we extracted from one particular device, and we found that for the certificate they use 163 elliptic curve. They've X, Y in this Gava field. The A is 0. For B coefficient they use square root of it to optimize the calculations, and the curve parameters confirmed by trial if the certain group order, and the base point was present in the host device with X and Y coordinates, and the public key was of one particular device is presented below. So for authentication, a different curve is used with the 2131 field, and A parameter is irrelevant because of the Montgomery methods. Again, the square root of the B coefficient is used because it helps to speed up the computation, and the curve is the same as in SEC2, and that was confirmed by trial. The group order we were unable to determine, and the base point is presented again only with the X coordinate because due to the Montgomery method, Y coordinates was irrelevant. And for one sample device, the public key is presented below with again only X coordinate that is required. So the authentication process looks the following way. So the secure element which is the device, stores the serial number, the base point, and the secret and public key, and the host also knows the base point and all the parameters necessary to compute to do the elliptic curve computation. So first it verifies the certificate. It requests the device to send the public key and the certificate. And after that, it generates the challenge, but also it scrambles the challenge to probably prevent someone to eavesdrop and easily find the parameters of the authentication. So the actual device unscrambles the challenge and then multiplies it with the secret key, and also the authentication process involves the MAC computation. So instead of sending back to the host the coordinates of the point, they send the MAC of that coordinate, and the host also calculates the MAC and compares the marks. So that again helps to randomize the authentication process and make any eavesdropping and side channel attacks more difficult. So we also tried to run side channel analysis on the device. So for that, we built a dedicated board with a resistor, but we found that a very high noise was present in the device operation. We looked at the spectrum and we found that the base frequency is about 8 megahertz with multiple harmonics, and the device contains side channel attacks, countermeasures against side channel attacks, the unstable internal clocks, the randomized ECC computation. So even if you send the same random challenge to the device, you always get the different response because they introduce the randomness into the multiplication process. Then we tried optical fault injection, but for that, the re-access to the device was necessary. The device is fabricated with somewhere between 1930 nanometer process, the 5 metal layers. However, there is no anti-tampering sensor on the device, so it is possible to probe the device, but accessing something below 3 metal layers is very tricky and time-consuming and expensive. So we had to approach the device from the rear side using infrared lasers. So we confirmed that the position of the memory in the device by deprocessing it. So we knew where the non-volatile memory is located, and then as you can see, there's no other memories on the device, and there are some analog blocks, and the rest is the logic. And then we use the SEM imaging to find the approximate size of the fabrication process. And also the optical microscopy doesn't help with that kind of device, so you're even unable to resolve any structures with optical microscopy. So the next step is we try to inject faults into the non-volatile memory in the hope that this memory contains some security critical components, either the key itself, so we can change a single bit of a key and see the change of the device operation, or it could contain some security features that would allow us to access the whole memory. And the advantage of laser fault injection is that the changes are temporary. So as long as the laser is switched on, you modify the device operation. And when you switch it off, the device is back to the original operation. However, the device needs to be prepared in a special way to be able to shine a laser at it. And because the device is very small, we had to reinforce the package with an extra epoxy and then polish it to the silicon substrate. And then we polished it even further to make the amount of photons reaching the actual device surface larger. So with the laser fault injection, you can see on the left top side the actual reading from the memory, and below it is what you read from the memory when the laser was switched on. So you can see sporadically some data change into FF. However, when the device was recycled with the reset, that's where all these changes are actually latched into the internal security control registers. So after several attempts, we ended up with the full access to the non-volatile memories. On the right top side, you can see the same device read with the security disabled. And there you can see the what the this is the counter. It became inverted, and then this is the ID of the device, and then it was followed by a constant that is shared between all the devices, and below it is the ECC curve parameter, the square root of the B, and then each device had a unique number at address A0 that we didn't know what it is at that time. However, when we looked at the physical memory of the device, we realized that there are much more data present. So we multiplied the number of rows with columns, and we ended up with the 672 bytes of present in the device, with extra 168 bytes used for error correction. And that's presumably because the single error correction, double error detection Hamming code was used. So we had to find a way to gain access to all this data, because we just realized that there's no secret key in 256 bytes that we were able to unlock. So we had to extract the private key, and hopefully we will be able to make 100% clone of the device. However, that task sounds like a mission impossible, because you have to go somewhere and you have no idea where to go, and you have to find something without any information where it is and how it looks like. So we had to reverse engineer the logic without actual reverse engineering, because if we wanted to extract the net list and reconstruct the schematic of the device, that would be a very time-consuming project. We wanted to find a much quicker way. Still, we know how to access the registers, and we know the concept of ENVM read and write access. So the question is, what else do we need to find the backdoor to be able to access the whole ENVM memory? The question is, are there any unused bits in existing registers? Are there any additional registers used in operation? Are there any registers with behavior that similar to the ones we know? And also, when we disable the security, does it affect the number of registers that can be used, and any other abnormal behavior of the device? So we scanned the whole register space, and we found all the registers with read access and read and write access. And also we did the same with the unlock device, with unlock security, and we found extra registers that became available for the read access and read write access. And then we did some probing of the registers with a bit of fuzzing, trying to write random data into different registers. And we ended up with a few dozens of devices damaged in that way. But that helped to find interesting registers. So, for example, we found a register at 270 address that was affecting the NVM access mode, and also that register was possible to use to reset the counter, the lifespan counter, because you can set bit 1 and it will write all zeros into that location, and that was corresponding to the largest value of the counter. And then was another register that was responsible for write protection on the user NVM area, which each bit protecting 8 bytes in the NVM. Other registers we found a 26F1 that was affecting the security of the device. If you set bit 6, for example, to 1, then the whole device becomes write protectable and not usable anymore. So you can also make a write protection of the counter, that register, and that register was always the bit 3 equals to 1, because that's the bit that controls the read access and the security of the device. So when we use a laser, we reset this bit 3 and get full access to the memory. But also we managed to find other registers that affected the access to the whole area of the non-volatile memory, and we called it extended non-volatile memory. So the register behaved in the same way as the standard NVM access, however, with the much larger address space, and the same use for the bits 6 and 7 that were previously found. So the register 266 actually gave us access to the extended NVM. And additional functions we also found is that some registers allowed us to also access the error correction bits, for example, register 270. And for this extended memory, the data buffers were different. So the larger 16-byte buffer was used, and the beyond it was the buffer for error correction codes. And there are separate different commands used for this extended NVM read and write, and that gave us access to all 672 bytes of data and 168 bytes of error correction code. So this is what the printout of the memory looked like with full access. So you can still see the first 512 bytes are the same as the standard NVM access. However, the second part of is all zeros. So below it, that looked like not the real data, but it's some kind of encrypted data. So we ended up with the situation where we can access the whole memory. And this is the memory that, as it's stored on the chip, but that memory is encrypted. So they do not store the secret key in the plain text. So we had to go further and find a way to break that protection. So we first looked at the Hamming code in the memory, how it's calculated. It's easy to extract by programming your own data and looking at the changes in the error correction. For memory encryption and decryption, each device is affected by the NVM value at A0 that was previously unknown to us. And then we found a register that actually enables the decryption of the area, and the decryption key is stored in another register, but it's only 8-bit, so it can be easily brute force. Also, the register 277 contains the copy of the device unique number. And on the reset, we found that the decryption key is actually derived from this number, and it's stored in this 278 register. So there's no need to brute force the key, this decryption key. So you just have to do the reading right after the reset of the device, and then you have everything set up. You just set the certain bit of the memory read register to tell the device that you want the decrypted memory rather than the actual physical memory. So after performing that...
Sergey, I just wanted to let you know we are running out of time, so you may want to hurry up.
Yeah, I only have a few slides left.
Okay, great.
So as you can see, we managed to decrypt the memory. So now we found the private key, and we can computed the private key multiplied by base point and confirm that it matches the public key. So that was the right key. However, you cannot easily modify that key because they also store the CRC of the encryption key. However, we found that CRC is a linear function. So if you XOR 2 keys and you XOR 2 CRCs, then you end up with the third key and the correct CRC. So this is an example of the secrets from the one compromised device, the public key, ID, signature, and recovered secret keys. The secret key they store on the device is only 128-bit, the 3 extra zeros. And so that allowed us to make the one-to-one clone of the device by reading all the data and writing those data into another blank device, and we ended up with two Optiga Trust B devices with exactly the same data, ID, and secrets, and that both devices were happily authenticated by the evaluation kit. So there are certain limitations to this approach, mainly caused by the laser fault injection. So it's not practical to do it with every single device. So we tried to find another way of speeding up the process, and in a hope to find a major security flaw that would give us 100 or 1,000 times speed up. And that means we have to find a non-invasive way. So that's was originally thought as a future research, but by the time I prepared the slides, that was already past work. So we found a way to modify the security of the device without actually involving any lasers. So it was purely non-invasive attacks without need to desolder the chip. It's very fast, so it only takes 0.1 second to disable security, 0.2 seconds to read all the data, and 0.6 seconds to write those data into another device. And that was caused by the certain security flaws in the memory implementation, but the full details will be disclosed and at a different conference by the end of the year, and have a full paper with it. So to conclude, we managed to do full reverse engineering and copying of the device without any NDA. We managed to extract all this information from the embedded memory, and we created fully working clone. So again, the hardware security has demonstrated its importance, and it highlighted the gap between the hardware and software in the way that the memory is controlled. And also we, again, would like to stress that the hardware security cannot rely on obscurity and lack of information. So determined attacker can always find extra information by looking at the host devices on the internet and so on. And very likely many semiconductor devices have backdoors, so determined attackers can find them. So for learning how to clone Optiga Trust B in less than a second, please stay tuned, and it will be disclosed soon. And yeah, thank you for your attention. I hope you enjoyed it.
Thank you, Sergey. As always, your talks are really mind-blowing and amazing to not just me, but to the hardware community as well. We have a lot of questions for you, but since we are already running out of time, we'll just take one question, and we'll take the remaining questions in the discussion room. So let me ask you the first question, Sergey, and then we can take the rest of the questions in the discussion room. The first question to you is from an attendee called as Teja. Infineon claims both Trust X and Trust M are EAL6 plus certified. Is it possible to do today's attack on Trust X and Trust M series as well?
We didn't look at those devices. I know that on Trust X device, you can find all the necessary information on GitHub, so you can start talking to those devices much easier without involving reverse engineering of the firmware. So in our project, it took us several months to do this firmware extraction and reverse engineering and learning about SWI interface. But in Optiga Trust X device, you don't need that. Everything is ready for you to start. So probably if you do the usual way of hardware security evaluation, you would be able to find something interesting, but that's probably a different project